going to start the lecture on nanotechnology and chemical engineering. So, today we will discuss about characterization techniques of nanomaterials. So, we already have discussed the BET surface area analysis, pore size, pore volume analysis. So, today the theory we have already discussed and few theory regarding in pore volumes and pore size measurements, the theory we will discuss. Also few numerical problems so related to the BET surface area, pore size, pore volume measurements. So, based on experiments how we can determine that experimentally, that we will discuss. Okay. So, already we have discussed that nanomaterials or nanoporous materials, so that is made of various type of pores, that may be micropores, mesopores or macropores. So, depending upon that we can characterize that materials which kind of or what type of material is there, and see if you are able to develop some materials having extremely high surface area or having extremely good pore or porosity is there, void is there, void space is there inside of that porous material. So, then material sometimes is very good for a particular applications, that may be wastewater treatment in terms of catalysis or in terms of mass transfer, heat transfer, many places it can be applicable depending upon their application. So, here we said already that different type of pores are available in porous material, that may be micropores, mesopores or macropores. So, depending upon that, so even nanomaterials, when we convert the bulk materials into nanomaterials, the surface area also increase drastically from very small surface area when it is bulk materials, and when it is in the form of nanomaterials, surface area increase extremely. So, now today we will discuss surface area measurement. So, here a few numerical examples will solve or will discuss. So, how we can measure with the help of BET equations. So, this is here you can see this is the BET equations. The theory details I am not going to discuss. So, that is included in these lectures, but I am not going to discuss step by step derivations of this equation. This is the final equations based on BET surface area measurement theory. Okay. So, these equations you have to use. So, here various parameters are there. So, this is the relative pressures and this is the monolayer volumes and some constants in these equations. So, here when we do the experiments, so we have to put that samples in a quartz tubes inside in that particular experimental setup. So, there is tube is there where we can put the known quantity of the samples. So, here in this particular question, so when we have taken a particular weight or amount of the samples, here catalyst weight or the materials weight that we have taken 0.1 grams, and then nitrogen gas by changing partial pressures. So, we are increasing the partial pressure from 50 to 500 millimeter mercury. So, that we are maintaining when absorptions experiment was conducted using that porous materials or catalyst. So, then the volumes get adsorbed over that material. So, that is gradually increase as we increase the pressure. So, that is experimental data we have obtained. So, using this data and these equations, so the specific surface area of this particular porous materials or the samples, powder samples we can measure. So, here initially this equations total surface area we can use here Vm N H, that terminology we have discussed in our previous class, and St is the total surface area and total amount of the materials we have taken. So, using here first you have to find out this is Vm, that is the monolayer volume. So, when particles or porous samples you have taken, so here this is the surface where these nitrogen molecules get adsorbed over there, and maybe monolayers or multilayer formations is there. So, the amount of the gas get adsorbed for these formations of monolayers. So, that you have to find out, and that would help us to find out the specific surface area of that material. So, here in this case first what we have to do, so this data we have. So, after that we have to means convert that data into P by P naughts and then this components. So, now this is the in the BET equations you see these components and these components. So, you have to find out from based on this experimental data, and then you have to plot this versus this. So, here we will get some slope and intercept from this line. So, once this data in x axis and this is in y axis. If we do plot, so then this type of line comes and then we can get slope and intercept, intercept from this graph. Okay. So once we have slope and intercept, so then this is the slope and this is the intercept from these equations. Okay. So these two equal components are present. This is the slope component and this is the intercept component. So slope 1 upon slope plus intercept, that is equals to Vm. So that will get, so from this experimental data slope we are getting an intercept from here. This is the slope, this component, and intercept as intercept, and this is the slope. So once we know then slope and intercepts, and then we can get monolar volumes, that is approximate this. Okay. So after that n equals to this means n number of molecules per moles for case nitrogen that at that particular temperature. So cross sections area of one nitrogen molecules that we can calculate by using some equations is there, that is the projected area. So for this temperature, so that much centimeter square per molecule. So 1 molecules of nitrogens that possess 1.62 into 10 to the minus 15 centimeter square, that is the cross sections area, and molar volumes of nitrogens that we can find out using this that way. So now this is the projected area of cross sections area. So these equations you have to use to find out this. Here m is the molecular weight of nitrogen, that is 28 gram per ml. Density of the nitrogen at this temperatures when it is in the form of liquids is this. So once we put this value, so then alpha or this projected area for one single molecules of nitrogens we can calculate, and after that similarly here's BT equations, BT experiment. So here's nitrogens is used as the adsorbing gas. So in this case projected area of nitrogens you have to calculate, and that you have to use here to find out the specific area. Instead of nitrogens we can use oxygens or other molecules also. So based on that projected area of O2 molecules we have to find out, and then we have to calculate the specific surface area of that particular porous materials or nanomaterials or catalyst. Okay. So here's once we know, so then Vm by V, V is there, Vm is here, V is here. So Vm by V into N's we can do, and then Vm by V into N's multiplied with A, that is the cross sections area we can multiply, then we can get total surface area. Okay. So total surface area we can get, and then specific surface area we can get, that is the materials, by dividing the total amount of the materials that was taken initially, that much quantity of the materials, porous materials or metal oxides that was taken. So divided by that, so then we can get a surface area that would come, that is total surface area. This is the specific surface area. So here's 412.6 meter square per grams. For that particular example you have taken, for that particular material specific surface area is this. So if we take different materials, similarly we can find out the volume of that nitrogen gas get adsorbed over the surface to different pressures by increasing pressures of that of nitrogen for adsorption. So at 77 kelvins. So we can find out different materials having different surface area. Here another examples also, porous silica gels that was taken, and we have to calculate the surface area per grams. Okay. Similarly, so in question 1 there, so we have used nitrogens, that gas was get adsorbed over the surface of the that catalyst that was taken 0.1 grams. So here's catalyst was taken 0.606 grams, and here's materials is silica gels, the surface area of silica gels that you have to find out, and here's oxygens was used as adsorbing gas. Okay. So in case of oxygens, so the projected surface area equations is this, I said this. So here alpha or A that you have to find out. Okay. So here molecular weight of oxygen, density of the oxygens that is given. Okay. So liquid density of liquid oxygens at this temperature is given. So density knowns, molecular weight is known, N is known. So then alpha projected surface area for this we can find out this, and then in Sg that we can find out. So Sg equals to this Vm or Sg or St, you can see total surface area both are same. So here's both are same. So here's this we can find out, and then monolayer volumes you can find out, monolayer volumes. So here's this 122 by using this slope and intercept. Slope and intercept is this. So using slope and intercepts, so from the BET equations, so you can find out this should be Vm per gram. So here's this is the weight that was used actually this. Okay, so then this way you can find out Vms, and Vms you can substitute here. V is known, N is known, A is known. So then total surface area or specific surface area you can find out, so that would be 465 meter square per gram. So in this case oxygens is used instead of nitrogens. So therefore density of the oxygen is known, and from the plots partial pressures and volumes of the gas adsorbed. So from there we have to draw this line. So means we have to plot that, this plot we need. Okay, so from the BET equations, once we get intercept and slopes, already we don't need to do these graphs. Actually the slope and intercept is given in this problem. So therefore directly we can put to get monolayer volumes, and once we know the volume, monolayer volume, then specific surface area and total surface area we can find out. So next there are few theory also, means for pore volumes distributions of the porous materials. So that capillary flow porometry by using weighting liquids like waters we can use these methods. That way also we can find out average pore volumes of that porous materials. And second one is the mercury intrusions porosimetry method. So here's non-weighting liquids that we can use. Here's helium mercury, means mercury, that is the non-weighting liquids that can use for this particular measurement of the pore volumes that is present in porous materials. Okay. So and third one is the gas adsorptions that already have discussed. So BET methods. So these are the initials methods, and after that this is most widely used and most widely accepted method. So that would give some more accurate measurements of pores volume, pore size, BET surface area. Okay, so here's in first method, so how we can measure the pore volumes, void volumes or solid density of that materials, porous materials. So here's in first methods I said weight, means we have to use waters. So that is the liquids, in this case weighting liquids I said in capillary flowmetry or weighting liquids. So that is the waters we have to use. In a solid samples first you have to take initial weight we know, and then so after putting water in that materials, some water will get adsorbed. Our suppose a materials is there, pore is there, and pore is filled with waters. Okay. So after that excess water that will be evaporated out, and then that water remain in the pores, that remains in that materials. So after that evaporations or drying, so we weight against. So then difference of weight is this. So this is it, S1 was the initial weight of the materials, S2 is the final weight of that materials once that water molecule get adsorbs or filled that pores. Okay. So then the difference would gives the amount of water get adsorbs in that particular pores. Okay. So this is actually S2 means final weight we know, so amount of water get adsorbs. So that is the difference would gives amount of water get adsorbs. And now if we know the density of water at that particular temperature divided, then we will get pore volume. So amount of water get adsorbed, so pore volume is easily measured. So and next one is that helium mercury methods. So in this methods also similarly, so in the materials, let us say we have, this is our materials, porous materials, this is pores or void space you can say. So this is solid and this is void. So when suppose we have a containers where a particular volumes of the gas is present, helium. So there if we put that material, so then materials, the helium gas will be filled that pores, and due to the solid weight excess amount of the helium will come out. So excess volume of helium, that is due to the total solid present in that materials, porous materials. So V3 we can get. Similarly same materials we have to placed in mercury. So there's mercury due to the additions of these materials in known quantity of volumes of mercury. So initial it was volume this and finally volume this due to the additions of solids. So excess volumes of mercury that will get due to the additions of the porous material. So since mercury would not fill that pores, helium will fill the pores, but mercury would not fill that. Mercury would not come or reach to the surface pores of that particular porous material. So excess volumes that is displaced by the additions of the materials in that mercury, so known volume. So here this is V4 and this is V3, so displaced amount of the gas or mercury. So here V4 is greater than V3, since here mercury would not trapped inside of that pores, but helium will trapped inside of the pores. Therefore the excess volumes will get in case of mercury when it is that materials will placed on mercury. Okay, so by that way actually we can find out, means if you know this amount of the volumes V3 and V4's displaced volumes is important. So if you know, and quantity of the materials, weight of that materials or particles weights, if you know, samples weight. So rho is, that is the density, materials weight divided by the displaced volume by helium. So that would give solid density, that is expressed in terms of rho s, solid density, kg per meter cube. So similarly if we from calculates rho p, that is the particle density, that included here the volume included with the solids as well as pores. So as the pores does not fill by the mercury, so here's displaced volumes V4s and MP amounts of materials that was taken. So density of that porous particles we can find out MP by V4, that is equals to kg per meter cube. So the density also materials we can find out by this two way. Even the amount of porosity that pore presents, I said in the porous materials there are different type of pores are present. So this porosity or white fractions, that also we can find out by these two methods. So if we know the materials weight, mass of the particle was taken, density of the solids and white volumes per grams of the particles, particle density that already have known, how that can be calculated by using these two methods. So if you know volume of the gas, white volumes per gram of the particles, that is Vg, at solid density if we know, so then white fractions we can find out. If is the white fractions by using helium displacements and mercury displacements also we can find out. So rho p is the particle density and Vg is the volumes of the gas, that is white volumes per gram of the particles if you know. So using this white fractions we can calculate. See here one example is showing numerical example. So in these two methods, so in first ones we have to determine the pore volumes or particle porosity. So that you have to determine is sample or the mass of the catalyst or materials that was taken, MP equals to 101.5 grams. And in helium displacement methods, the volumes of the helium that is displaced by the sample, that was this, and when volume of the mercury that was displaced by the samples, that was this. So here you can see this is V4, I said this is V3. So volumes of helium displaced amount would be less and volumes of mercury that would be displaced by the samples would be more. Okay. So now Vg, that is the pore volume, so that we can find out that difference between V3 and V4 is this, and the amount of that materials that was taken 101.5 grams. So then this would be pore volumes of that material. So if you know V3, V4 and amount of the material was taken, so pore volumes easily we can find out using these methods. Okay. So even porosity also we can measure if we know the solid density easily we can measure. So amount of the materials that in terms of the grams we know, and volumes that is helium displaced 45.1. So then density of the materials we can find out if you know the density, and Vg, that is the pore volumes. So here's Vg is the pore volumes or white volumes per gram of the samples. So pore volumes multiplied with this solid density and divided by this, and we can get the porosity. So by using this data, so using the volumes displaced by the helium volume displaced by the materials that we can use to calculate porosity by using this equation. Similarly, another equations for these equations also we can use. If you know the particle density and void volumes or pore volumes, so that pore volumes that already you have calculated by using the difference volumes by mercury and helium volume that is displaced by the sample, and particle density that usually you can find out, and then the both way we are getting the porosity of that materials, that is approximate 0.455. Okay. So, now porous radius calculations. So, there are mercury penetrations method also that is available, and see here by using the force balance. So, if we apply some force, the force equals to due to the surface tension. So, here some angles is there, and this is the pores radius diameter to A. So, pore radius is A, small a. So, here's cross sections area, that is pi r square, and applied force pressures is this, pressure equals to force per unit area. So, force balance we are doing. So, that equals to the force due to the surface tension is this, and force due to the applied pressures. Okay. So, here's these equations we can use. So, to find out the porous radius, the force is not in this particular method, mercury penetrations method. So, here if you know the contact angles, this is the theta, and this is the applied pressures. If you know surface tension of mercury that we know, so then we can find out the pore radius or pore diameters that we can find out. So, in this particular methods, mercury penetration method, there is some limitations. So, we cannot accurately measure the pore smaller than 10 nanometers. If suppose materials having different type of pores, I said micropores, mesopores, macropores. So, if it is less than 10 nanometers, then we are not able to find out the pore structure or pore diameters or pore radius, that we cannot find out. So, this is the limitations. So, means pore may be 0 to 100 nanometers pore. So, if it is 10 nanometer, less than 10 nanometers, so then these pores we cannot find out, but more than this we can find out. So, this is the limitation of this particular study. Okay. Then nitrogen desorption method already have discussed. So, in this methods we can measure easily the pores having less than 20 nanometers or 10 nanometers also easily you can find out. Means if suppose pore radius having 20 nanometers, we can find out 5 nanometers easily we can find out, 0.1 nanometers easily we can find out. So, smaller diameters, pores with smaller diameters or less than 20 nanometers. So, any kinds of pores we can find out easily by using this nitrogen desorption methods. Okay. So, in this methods actually already we discussed. So, here in this there is some theory, that is the Kelvin equations is there to find out the pore radius. So, A minus delta, A is the pore radius and delta is the thickness, actually thickness of the monolayer adsorb. So, when gas is adsorbed, let us say this is our surface of the pore, this is the pores, this is the solids and this is the pores actually. So, these pores having some radius, so that we are going to find out, this is A. So, when nitrogen molecules get adsorbed, so here's monolayer formation should be there, this is the monolayer formation. So, this is let us say thickness delta formations is there, that is the thickness of the monolayer that is get adsorbed. So, that is due to the nitrogen molecules. So, if this actually balanced A minus delta. Okay. So, whenever A we want to get, A is the actual, that is the pores of that materials or porous diameters, pore materials diameters, okay, in terms of nanometers. So, if you want to, then we have to add the thickness of monolayer thickness, so that you have to find out. So, using this equation. So, for liquid nitrogens you said here's by simplifications all components, molar volumes of the condensed liquids, contact angles between surface and condensates, and surface tensions of liquid nitrogen. So, then after simplification or putting all these components, so you can get this equation, simplified equations. Here P naught by P, that is easily we can get from the BT experiments. Okay. So, then we can put that value in that relative pressures, and then A we can easily find out. Okay. So, here's average pore volume. So, here's you can see, so average pore volumes we can find out. So, that was, this is the molar volumes of the liquid nitrogens, and this is the amount of the gas get adsorbed here. That is from the BT experiments we can find out the amount of the gas is required to fill all these pores. So then let us say this pores is there, so this amount of that volumes of the gas, that is Vg, that easily we can know from the BT experiments. So Vg was know, so then molar volumes we know, and then Vp, that is the average pore volumes, that we can calculate. So using Vg is known, Vg is equals to this per gram catalyst, this is the amount of the volumes of that gas adsorbs to fill that pores, and molar volumes we know. So then average pore volume, so this average pore volumes, this is average pore volume Vp. So of that porous materials easily we can find out. Okay, and what is the density of liquid nitrogens, molecular of liquid nitrogens, and molar volumes, how to find out, that is given here. So you can see to calculate average pore volume by using BT experiments. Okay, BT theory or experiments we easily can find out. Okay, then pore radius also similarly Kelvin equations I said, Kelvin equations also we can find out. So here you can see that is the pore radius and pore diameters, this is pore diameters and this is pore radius. So the equations I said, this equation same equations. So here we can find out by putting all components. So Rp minus T equals to this is coming here, it is expressed in terms of T, means thickness, adsorbed film thickness or monolayer volume thickness, monolayer thickness, this is. So that can be calculated by using these expressions, and so once we know that T value or delta, T or delta both are same, so that once we know, so that we can put, and then Rp, that is the pore radius, that we can measures by using these equations. Okay, so here it is given by considering different P by P0, here P by P0 was taken, so this. Okay, so it depends actually on the experiment. Actually if you notice the experiment, so experimental results we are getting, so they are actually from the experiment the volume get adsorbs with relative this is the volumes pressures and this is the volumes, so amount of the gas gets adsorbed. So from this P by P naughts we can find out, this P by P naughts we have to put in that expressions. Okay, so P by P naught, so at different relative pressures, so what would be that, here P by P naughts, that we can substitute or we can place here to find out the pore radius. Here also this or here you can see that relative pressures that we can put at that specific pressures, the amount of the gas adsorbs and which particular pores is there, pore radius easily we can find out, pore volumes we can find out, specific surface area we can find out. So by using BT equation, that is the most widely theory. So apart from that there are others method also, that also we can use, but in few methods there are some limitations. So therefore most widely accepted any type of pores in porous materials we can find out BT experimental or theory. So from there, okay, so here the BT theory is given, so the details I am not going to discuss, so you can study that. Okay, so the theory is developed, so how that BT equations actually finally developed, so these equations actually. Okay, so step by step methods for means monolayer formations, then multilayer formations, these final expressions how that has been come, so that has been given here, so you can study. Okay, so thank you. So today is up to this. Okay.